Hello there, this is Alana Tuckey, and in this tutorial video I'm going to go over the section 5.4 notes, namely about conditional probability and the general multiplication rule. So we're going to begin with conditional probability. Now conditional probability has a different notation than the probability notations we've seen before. Instead of just P, which stands for probability, parentheses of F, right, an event F, which stands for a probability function. Probability of F or the probability of E. For conditional probability, it's the probability of F given event E. In other words, event E has already occurred, so now what's the chances of event F? So let's do an example and see if this makes sense. So we start off with, we have two six-sided dice, one red and one white. And then we toss the red die before we toss the white die. And that's why the red die is in the first position in all the pictures and the white die is in the second position in all the pictures. Now before we toss the dice, when you're having them sit in your hand, what is the probability that the the faces sum to 5? Well, we already learned that probability. When you're looking for the sum of 5, you want 4 and 1, which is right here, or 3 and 2, or 2 and 3, or 1 and 4. So there's 4 ways that can happen out of 36. And 4 out of 36 reduces to 1 over 9, which is 0.1 repeating. And notice this is a review question from 5.1. This is not a conditional probability question. This is just a reminder of how this works. All right, now how does that compare to a conditional probability question? So the letter B is one of those. You roll the red die and it comes up 1. With the white die in your hand, what is the probability that the faces will sum to 5 now? Write the probability in symbolic notation. Okay, so you roll the red die and it comes up 1. That means that automatically you're only going to look at the top row, because the red die is 1 means all the other rows, the red die is 2, 3, 4, 5, 6, have to all be discounted. You've rolled a 1. So that means with the white die sitting in your hand, these 6 options up here at the top are your only 6 options. So what's the probability that you sum to 5 now? Well, the only sum of 5 with a red of 1 is right here. It's 4 and 1. So we want the probability that we roll a sum of 5 given that the red die is a 1. The way to write that with symbols is a capital P for probability, and then you write out sum to 5, because that's what you want. You want to sum to 5, given that the first die is a 1, or the red die, if you will. Okay, well, the red die being 1 means you only have 6 options, so your denominator is not going to be 36, because, well, 30 of the options are off the table for you. The second row, third row, fourth row, fifth row, sixth row, they're all gone. The only row that you can even look at is the top row at the top, which I realize is slightly redundant. Bear with me here. So we have our top row. I've highlighted it for you in blue, and there's 6 options there, and only one of those options, the 1 and 4, adds up to 5. So our probability is going to be 1 divided by 6. Which gives us a probability of 1/6 or 0.16, where the 6 is repeating. Now notice these probabilities are significantly different. The probability that they just add up to 5 naturally, there's 4 out of 36. But the probability that they add to 5, given that you've already rolled a 1, is a very different proposition. All right, so now we just learned our first rule. It's the conditional probability rule. It says if E and F are any 2 events, then the probability of F given E, that's what that little vertical line means, given that, is the probability of E and F divided by the probability of E. Right? In other words, the number of ways that both E and F can occur divided by the number of ways E can occur. Let's think about this last one in particular, the one with the N. N stands for number of ways. So when you look at what we just did, we actually did this last part right here. The number of ways that you can sum to 5, right, and have the first die be 1. Well, sum to 5 and the first die is 1 is the 1, 4 right here at the top, right in the middle. And then divided by the number of ways that event E can occur. Well, event E for us was the first die is a 1, and that means there's 6 of them, and that's what we've highlighted with the little box right there. All right, let's take our knowledge and apply it to a new problem. Let's look at poker cards, standard poker deck. So first of all, what is the probability that you have a diamond? Well, that's not a hard probability to calculate at all. There's 13 diamonds out of 52. So the probability of diamond is 13 out of 52, which is, everybody knows, 1/4, because a fourth of the deck would be a diamonds, which is 0.25. So far, so good, right? That's an old question that we've seen before. Now, suppose you catch a glimpse of the card being dealt and you know that it's red. Okay, so dealers passing out cards, and you just out of the corner of your eye you can tell that it was you or somebody, maybe an opponent, was dealt a red card. Now, what is the probability that the card given is a diamond, given that you know that it's a red card because you caught a glimpse of red from the dealer's hand? So you know it's red. What's the chances of it being a diamond? Okay, well, that's a conditional probability because of the given that part, right? The fact that you know that it's a red card. Okay, so we want the probability of diamond given that. So to symbologically show given that, we use a vertical line. So given that the card is red. Okay, so now we have to think about how many cards are both diamonds and red. Well, that's 13, divided by how many cards are both red. So let me write that up. The number of cards that are diamond and red divided by the number of cards that are just red. Okay, well, there's 13 diamond and red cards. All the diamonds are already red, so all 13 of those are going to count. Divided by how many red cards there are. Well, there aren't 56 red cards. There's only 26 red cards, and that gives us a half, which is 0.5. And we can apply the same logic here that we used for this symbology here, the number of diamonds and red divided by the number of reds, because what we're using is that back part of that formula. We can actually go back here and do the same thing with the die. Like I said before, the number of ways that it was both sum of 5 and the first die is 1, which was only one way, divided by the number of ways that the first die was 1, which is 6. Just to put that extra notation in there for you. So you're used to seeing this notation that you're seeing in the back half of that formula. All right, so let's go do poker hands again, just one more time. All right, this P parentheses queen. Well, that's the probability of finding pulling a single card and having it be a queen. So that's the words. Let me type that up. There. This is the probability of that, excuse me, P parentheses queen is the probability that a randomly selected card from a poker deck is a queen. All right, now we're going to find it. Well, it's not too hard to find because there are 4 queen cards, 4 Q cards in a standard deck. So it's just going to be 4 divided by 52. Which is 1 out of 13, which in a decimal is about 0.07, in case you're interested, 0.0769. This is not one that has a repeating decimal pattern, so we wouldn't be able to figure that out for it. So I just rounded to 4 decimal places. All right, great. So that seems pretty straightforward. That's stuff we learned how to do in section 5.1. But now we're going to take it a step further. They put the queen and they have this vertical bar in there, and then they have face. So that's saying, what's the probability of drawing a queen given that you know that it was a face card? Now, I have to be honest with you, I've played several games of cards with my family, although we generally play pinochle, not poker. So I have caught glimpses of cards that are being dealt out by the dealer, and I can tell that it's a face card, even though I'm not sure what face it is. So it's the probability that a randomly selected card from a poker deck is a queen, given that you know, or given that we know, it is a face card. Or how about this, instead of we know, given that it is a face card. Okay, so given that you were passed a face card, or you're a relative that you want to beat at the card game was passed a face card, what's the chances that they were given a queen? Okay, now we're going to find it. Well, it's the number of ways that you can have both a queen and a face card divided by the number of ways that you can have a face card. So let me write that up. So it's the probability of queen given face is the number of ways you can have queen and face divided by the number of ways you can have face for a single card. And again, I'm using queen and face there in place of E and F from the problem, or from the formula, excuse me. So the number of ways that I can have both queen and face, E, which is F and E, technically I'm going in reverse, divided by the number of ways I can have a face card. In other words, you can kind of think of it logically. You know that it's a face card. Once you see the face card going out to your relative or your competitor or yourself, then you know there's only 12 possible cards this could have been. And then how many cards of those are queens? Well, there's 4 of them. So there are 4 queen and face cards, namely the 4 queens, divided by how many face cards there were. Because once they pass out that card, you know it's not a 7 or a 10. You know it's a face. It means there's only 12 possibilities it could be. That's a significantly different thing than just knowing it's a queen. I mean, a queen is 4 out of 52, but once you catch that glimpse that it's a face card, that significantly lowers the pool of cards it could be from 52 to 12. And 12 is a much smaller number. Right? And therefore, it's drastically affecting the probability. I mean, notice, if you don't have a clue, the chance of just getting a queen is 0.0769, 0.077. But if you catch a glimpse and see that it's face, then the chances of it being a queen from that point is what? Triple? Almost triple that, right? 0.07 times 3 is 0.028 or 0.28, and we're above that. So it significantly changes your chances. That's why people always want to cheat at cards, right? Because they want to have better odds and better probability of winning. And I'll pause right there, and I'll come back in the next video with the next example.